Good morning, everyone. My name is Wagner Moraes. I am firefighter in Brazil. So in Brazil, by our constitution, each state is responsible to organize the fire service. So just as an introduction, we have all the four stages of a cycle. So we do the fire safety code, we fiscalize its appliance. If something gets wrong, we fight the fire, obviously, and after fight the fire, we do the fire investigation. So with that information, we can feedback all other stages. So this work I'm going to present is Uncoordinated Egress and Experiment. So from 2013 Brazil, the Kiss nightclub tragedy was caused by the leader of a band who lighted fireworks. Sparks fired the polyurethane sound insulation on the roof. Fire spread quickly and released poisoning smoke, causing the death of 242 persons. I think you were aware of this 3 years ago about. There were internal obstacles, poor escape signaling, and only a front door available for evacuation. People blocked that door, striving for their lives. Firemen and volunteers tried to open another means of escape from the outside wall, in vain. As a lesson learned, we firefighters of Santa Catarina, as I told, we are responsible for the fire safety code in our circumscription. So we did some changes regarding to the nightclubs and similar occupation. Fireworks and polyurethane-like insulation were prohibited. So what about the door size? Was it necessary to increase its width? That's a question, right? So the door size for nightclubs used to be designed like this. Area defines allowed population. Allowed population defines the total door width in order to accomplish an evacuation performance. So here's a question, right? Are the calculus enough safe for an uncoordinated egress like the one took place at Kiss nightclub? So according to these authors, so this is these authors, Helbing, Farkas and Vicsek, is simulating dynamical features of escape panic, was publicized in Nature 407, I think it was 2000. So, according to these authors, in an uncoordinated egress, the following are observed. People move faster and start pushing. Moving become uncoordinated, so the turbulence. Arcing and clogging at exits can appear. Jams build up, pressures become dangerous. Escape is further slowed by fallen or injured people. People show a tendency toward mass behavior. Alternative exits are often overlooked or not efficiently used. So, the same paper provides this simulation plot. So, they provided us that model that has this simple interface. The model considers psychological and physical interaction among individuals. We use the parameters set as default. I received this model and just use this as I received. As some of you already noticed, and some of you told yesterday and the day before, regulators like me are normally quite skeptical about such video game simulation, right? That's why we did an experiment. In a 70 square meter area, we positioned firefighters trainee. So at the beginning, everyone was good spread around, right? At the sound of a whistle, everyone was rushed to this 1.12 meters door. We positioned 3 cameras. One at the crowd's back, the other one above the door, over the door, and the last one from outside. So here, from the back of the crowd, above the door, and from outside. Look, this is just 1.12 meters door. This is what we get. So as a military firefighter, you receive an order, you look to the aim, and you do this as fast as you can. So because the key is plot, we had not too much time to decide about the door size in our code. That's why. So let's check the video. You can see the turbulence. Somehow they go to the left, to the right, some blockage, people press it against the wall. From outside, many of them are hurting arms, hurting hands, and I've been chilled out about that. So, oh no. Right? So, this is a snapshot of a part of that video. So, let's see. This is possible to see that individuals are compact body to body in these 2 lines, from here until the wall. So, as people from behind keep pressure for getting out, it compacts, and the pressure rise up until it's broke. It has been broken, and a lot of them can escape. Then, after a while, another blockage forms. So the crowd turbulence, we could see on the video that some individuals go to the right, to the left. I focused on the tallest and heaviest individual. So this is overlay of several snapshots, and the numbers represent the head of this individual. He started from here, 2, 3, 4, 5, and then go to the left. And then by the left, go to the right. You can see in the video that, imagine that with this individual would be another person, like a girlfriend, a mother, or someone that he cares about. If he goes to like this and miss the person, it could cause reentrance from this guy. After getting out, the place would like to come back. It would increase the delay of the evacuation. So, another video. So it's like simulating a party, you know, so that's why. The guy I've talking about is this one here. See, to the right, then to the left, and then here. He's really tall and heavy, you know. So, as quantitative results, we focus on the mean flow. The mean flow, right? Egress mean flow. So, IN09 is our normative instruction that deals about the escaping, right? For coordinated egress, that would be expected in many fire safety codes, the mean flow for a door 1.12 meters would be 3.33 individuals per second, right? But in our experiment, uncoordinated egress, we can see up to 104 individuals, that means 2 individuals square meter, we have a higher mean flow, right? So that means up to 2 individuals square meter, we have faster egress than expected by the fire safety code. Another thing that we have to consider here is for this one, 208 individuals, that means 4 individuals square meter. At this experiment, the mean flow gets out of the tendency to lower, is higher than the previous one. So we checked the video, and we noticed that individuals realized that if they push, they last longer inside. So we increased the evacuation time by reducing this pressure about 20%, as it would be expected by the tendency. So actually, I wasn't aware during the experiment, but they did it. They realized, because the last experiment, so it's 208 persons, so I had to repeat some of them. And I think they, hey, stop pushing, so we go faster, or we won't get hurt. So they cheated me, but I got an information about that, so that's the science as well. So comparing experiment results against that simulation from nature, that simulation I showed you. So for 0.5 individual square meter, it fits quite kind of, hey, what you did, you were cheating with the numbers. No, I just take this, and it's quite good. But not so good the other ones, right? So here, experiment in blue color, and the red color, simulation. 1, 1.5, 2, 2.5, 3, and 4. So what we did with this simulation, once we realized that it's quite good with our experiment, so they are not so skeptical as before. So okay, the video game, it works. They realize that, right? Okay, let's play with this. So we did a simulation with the keys area. Keys area is about 600 square meter, right? So it would be expected that the allowed population should be 1,200. With this population, we calculated with our normative that we need 6.76 meters total door size, right? So here in yellow color is what would be the evacuation plot for a coordinated egress, about 60 minutes, right? And simulating 2 doors at the same size, we receive, 3 doors at the same size of 2.26 meter, we receive half of this time, right? And even if we use just 2 doors larger than that, so it's even faster, the evacuation. Conclusion. For uncoordinated egress experiment, the arcs and turbulence were observed. The greater the crowd, the lower the egress flow rate. When crowd stops pushing, flow rate increase. On the simulation, although simplified, model fits enough for us, the experiment. And we conclude the door with applicable in our state is safe. So that is a quite aimed experiment and the result in normative in our fire safety code. That's it, I think.
Thank you. We have time for a question if there's here. Okay, and I'll come back.
Thanks a lot. You brought up, I think, a really good point at the start, and people tend to go through the doors that came through, or the door that they got into large assembly space with. There's requirements in the IBC and FPA 101 that requires the entrance door, if there's one entrance or a main entrance, to be sized for half the width of the required width. Is there any requirement like that in Brazil?
I did not understand.
You were up like in the start of your presentation. You said that occupants they tend to not go to all the exits. They only went to certain exits, like the door they entered through. In some building codes require that your egress width, half of it has to be the door you entered through. Is there anything like that in Brazil?
Yeah, I'm not sure I understand your question, but I mean the firefighters, you are talking about the firefighter trying to open a mean of escape on the wall? It's like this, or?
Yeah, I can discuss later.
Right.
Yeah.
Okay, I understand. Now Portuguese is even better for me. Sorry, man, sorry. We have this in our national regulation, but the national regulation is actually lower than our state regulation because it's just kind of not law. For us, in the state is law, but it's just recommendation for engineering, that national regulation, right? So we have kind of that deals with part of this goes for the main trains, parts of goes to the second and third trains. But for us in our state, we don't deal with that. We just design for the sum of the width of all doors, right? We sum of it. And we had to distribute this for quite of, actually today is 70%. We take the main diagonal, the main diagonal of the place, from there to there, and 70% of this distance should be the distance between two doors. Just this. I know, I don't think if I... All right, that's better.
I have another question. You have shown these very interesting experiments that you conducted mostly with military people, so trained male population.
There were some women as well.
Yeah, but mostly
10%.
military people.
Okay.
Do you want to comment on the fact on how can you do a direct comparison between an evacuation in a nightclub in which you have a variation of type of people that might be intoxicated? There may be many different factors of making them not being the same type of population that you had in your experiments. So how did you take into consideration the fact of the differences in population comparing, let's say, the ideal case and instead the actual type of population?
Right. Our focus was in the physical dynamics. They are very skeptical about this, so I said, so if we can take the best fit man here and try to escape, you will see this. Okay, let's check. And that's why we are not consider fire, smoke, and so on. So just focus on the physical interaction between bodies. So, but it was 3 years ago, I made the final report for firefighting after 2 years firefighting studies, right? And there is 90 pages, it's much more than I present here. So there we consider what would be, we can talk later, I can show the work as well, so it's better.
Thank you very much.
I think.